Welcome back, geometry students, as we continue our units going inside triangles with all the beauty and majesty that lies within. We've already covered mid-segments and perpendicular and angle bisectors. Now we're going to talk about other bisectors inside the triangles and see what relationships they have. So fun stuff awaits. We're going to talk about bisectors and triangles. So in this lesson, we're going to discuss what the circumcenter and incenter is. Yay, vocabulary. How to find the circumcenter of a triangle. How to use the circumcenter of a triangle. Hooray for real-world applications. And identifying and using the incenter of a triangle. So let's begin where we normally do with notes. Woohoo! So this is the hard part right here, is the notes, because we're getting into some interesting words, right? And it's all about vocabulary in this class in particular. And so this set of notes has difficult vocabulary. So this is a point to pause and copy and write stuff down and make sure you're building your vocab up through the good notes that you're taking. The first note I want to talk about is this theorem that talks about concurrency of perpendicular bisectors theorem. It's not so much that we're going to use it, but it helps to build vocab. So we have this thing called the circumcenter that this particular theorem discusses. The circumcenter is basically the center of a circle that goes around the triangle, that is circumscribed around the vertices of a triangle. And that's what a circumcenter is, the center of a circle around the triangle. So how can we find a circumcenter? By using perpendicular bisectors. So each segment of a triangle, right, there's 3 segments. Each segment has a perpendicular bisector, which goes back to the previous lesson we've done, where all those perpendicular bisectors meet, or also known as the point of concurrency. Okay, that's a new vocab word. What does concurrency mean? Where everything meets. Okay, so concurrency is where everything meets. So the point of concurrency of perpendicular bisectors is called the circumcenter. And that's the first note. So when we look at the diagram, here's our perpendicular bisector for AB, and here's the perpendicular bisector for AC, and here's the perpendicular bisector for BC, and boop, boop, they all meet at point P, right? Point P is the circumcenter around the whole triangle. And then we can do a quick demonstration of that using a compass. Here's how, right? So you put the center of the compass at point P, and you move the compass to one of the vertices, right? And then, woo, as you draw the circle around, guess what it's going to touch? If I was more precise than think, it would touch all the vertices, right? So anyway, that's called the circumcenter. Okay, so the center of the circle around the triangle. And the circumcenter is made from perpendicular bisectors. Perpendicular bisectors, circumcenter. Circumcenter, perpendicular bisectors. Okay? Okay, next note. The incenter. Whoa. What is this? Okay, so the incenter is the center of a circle that fits inside the triangle, also known as inscribed. Okay, more vocabulary. So the incenter is the center of a circle inside the triangle. How is that found? By angle bisectors. Okay, so notice previously we had perpendicular bisectors. Boop, boop, boop. Well, now if we cut the angles, we bisect the angles where those things meet, where those rays meet, that point of concurrency, right, where everything meets, that is the incenter, the center inside the circle. And again, a proof, right? So if we have all of these angle bisectors, cut in angle B, and cut in angle A, and cut in angle C, C congruent, congruent, bisected, boom, boom, bisected, boom, boom, bisected, where they all meet, point P. And they are equidistant from the edges, right? So I can find the point on the compass and then inscribe a circle. Now, if I was more precise, it would have been better. But you can see how that works. Okay, so it's equidistant because a radius stays the same from a given circle point, right? So those are your notes. Incenter, angle bisector. Circumcenter, perpendicular bisector. And make sure that we know the difference. Okay, as I talked about before, vocabulary in this class is where your eyes go. And now I'm going to show you a quick cheat sheet, courtesy of my rock star colleague, Miss Krista Book. She teaches geometry with me at this school. She came up with this neat little cheat sheet for all the other vocabulary we're going to use. But This is such a neat diagram here. We have this thing. How do I remember these things? Well, if you can remember a purple bear circus, the perpendicular bisector is the circumcenter, and that there are angry birds inside. So angle bisectors make the incenter, right? So like imagine this is a purple circus, and then there's angry birds inside of it. So purple bear circus, angry birds inside, and you can recall how we can know that the circumcenter is made from perpendicular bisectors intersecting, and the incenter is made from angle bisectors intersecting. And so we can see a few more cheats there where things must start, right? Perpendicular bisectors don't have to be at a vertex. Angle bisectors do. There's some locations of where these things would be depending on the type of triangles, if we're dealing with acute, obtuse, or right. Diagrams of what the bisectors might look like, and then some cool facts. So we talked about circumcenter and incenter. So those are the notes, right? Let's get some work done, shall we? So here's an example of a question. We're going to find the circumcenter of a triangle, and the question may look like this. What are the coordinates of the circumcenter of a triangle with vertices at 0, 6, 0, 0, and 4, 0? And so in this particular example, we're lucky enough to have a diagram. So we have 0, 6, 0, 0, and 4, 0. Where are the coordinates of the circumcenter? And so again, how am I going to find the circumcenter? How do I remember? Well, remember Purple Bear Circus, right, from this book. So we have the circumcenter. We're talking about perpendicular bisectors. So now we look at this diagram, and we're thinking, whoa, how am I going to find the perpendicular bisectors from this picture, from this diagram? Well, we have to remember what a perpendicular bisector is. Well, we remember what bisect means. Cut in half, right? Bisector means half, and then the perpendicular means, well, perpendicular to it. So just take, for example, the segment down here from 0, 0 to 4, 0. If we take that segment, it's 4 units long, correct? What would half of that be? Half of that would be here, okay? Now, this particular segment is a horizontal segment. What's perpendicular to horizontal? Vertical. That's just a basic thing, right? So perpendicular to horizontal is vertical. And so we are thinking of a vertical line going through the halfway point, going through the midpoint. That would be our perpendicular bisector. And so we could, trace or use the grid paper, no matter. Right? So that would be the perpendicular bisector of the base. Now, if the circumcenter is the point of concurrency, right, we just need to find one more perpendicular bisector, and we'll know the point of concurrency. So which perpendicular bisector could we find? Could we find this one here, or could we find this one here? Well, look, from 0, 0 to 0, 6, that's easy to count, right? And it's also easy to know perpendicular, because this is vertical. Perpendicular to vertical is horizontal. Okay, so on the flip side, perpendicular to vertical is horizontal. And that is a fun fact to know. Okay, so perpendicular to vertical is horizontal. So if we have a vertical line, let's find the perpendicular bisector. Again, bisector means cut in half, right? So we have 1, 2, 3, 4, 5, 6. Well, halfway. Boop, boop. Right, so there's halfway. And this is a vertical line, so perpendicular would be horizontal. So we could, sketch, or we could follow the graph paper, no matter. Now, do we need to, we have our perpendicular bisector there. And remember, we're looking for the point of concurrency, the circumcenter, and for Purple Bear Circus, right? And so we need all 3 perpendicular bisectors, don't we? Don't we? Do we need all 3? No. Okay, so we don't, because if we have 2, we have 3. It's a point of concurrency. So we don't need 3. 2 will do. Okay, we don't need 3. 2 will do, because it's the point of concurrency. So the third one must meet there as well, which means in this case, the point of concurrency is located right there. Boop. And that is the circumcenter. Okay, so what are the coordinates of that particular point? It is 2 on the x and 3 on the y. So it is 2 on the x, 3 on the y. There are the coordinates of our circumcenter. Okay, and that's how we find a circumcenter. Yay! That was easier. Well, maybe not. It's not easy. I give up. That's not easy at all. Let's just do some more practice. That'll make it easier. So check this noise. Let's do another example, but I'm not going to give you a picture. What are the coordinates of the circumcenter of a triangle with vertices at 2, 7, 10, 7, 10, 3? Well, where are these points? So let's find them. We got 2, 7. So 1, 2 on the x, 1, 2, 3, 4, 5, 6, 7 on the y, and that is point A. We've got 10, 7, which would be out here, and that would be point B. And then we have 10, 3, which is out here, and that would be point C. Okay, so we would have the triangle. We have the triangle located there, and so we could see where the triangle is at. All we got to do is find the circumcenter, or also known as the point of concurrency for perpendicular bisectors. So remember from the last example, if we had vertical and horizontal lines, then we could find the perpendicular bisector, cut it in half, and go horizontal to my vertical, or back and forth. So we can do that very same trick right here. Okay, so if we have a horizontal segment, and this segment has how many units? We have 1, 2, 3, 4, 5, 6, 7, 8 segments. 4 cuts it in half. So 1, 2, 3, 4. That's going to cut it in half. And so we would have our perpendicular bisector that way. Okay? And then the other segment, the vertical segment, well, how many units? 1, 2, 3, 4. 2 cuts it in half. And so we count 1, 2. Okay, so we can see this is our perpendicular bisector. And so again, we're asking for the points of concurrency, the circumcenter of where those perpendicular bisectors would intersect. It would be right here. So the only question is, where in the world is that? So where in the world is this ordered pair? 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5. Interesting, it's at 6, 5. So the coordinates of the circumcenter are at 6, 5. And that's how that works, right? Through coordinate geometry and knowing what's going on. Remember, purple bear circus. Yay. More examples. How about real world stuff? Well, as real world as we can make it currently, a town planner wants to locate a new fire station equidistant from the elementary, middle, and high school. Where should we locate the station? So this is what's kind of neat about this question. We have an elementary school located here. We have a middle school located here, and a high school here. And the question is, where would equidistant to all three be? Equidistant would be if each of those had the same radius, right? If there was some kind of center where the radius would be the same, that would be equidistant. Okay? So we got to think, if there were a circle that had the same radius, that's a neat thing to think. Guess what a circle with an equal radius would look like? It would look like, with all three of these locations, something like, something like that. And that would have to be our location where the radius would be the same, right? So if we can think about that, we could then think, hey, well, if these three locations make a triangle, right? And seriously, you do want a fire station as equidistant to these schools as possible, okay? You have a triangle. If we find the circumcenter, we're all set. So where should he locate the station? At the circumcenter. So that's where he should locate the fire station. If we have the perpendicular bisector, right? If we found the perpendicular bisector of here, and then the perpendicular bisector of here, and then the perpendicular bisector of here, we would have the circumcenter, and that would be equidistant. Okay, so we want the perpendicular bisectors of each segment, and then we would find out exactly where the circumcenter would be. Okay, so in this case, we could use constructions or whatever. That's basically, it's a vocabulary question. A question like this is vocab. Okay, and we'll see what it might look like on a quick quiz later. So a very similar question, right? Town planner wants to place a bench equidistant from 3 trees in the park. So we have these 3 trees. Where should you place the bench? It's the same question. Imagine a bench that would be the center of some kind of circle, right? And imagine a circle like that. How could we find the center of that circle? The way we find the center of that circle is to make a triangle from the 3 points. Make a triangle from the 3 points. At each point, find your perpendicular bisector. Okay, perpendicular bisector and perpendicular bisector. They would meet at the point of concurrency, the center of the circle, the circumcenter. Okay, so again, where should he put it? The circumcenter, the point of concurrency of angle bisectors. Okay, so that's the big, or not angle bisectors, I meant perpendicular bisectors. So purple bear circus. So you got to remember that note. So the circumcenter is where the perpendicular bisectors meet. Okay, are we cool at circumcenter and perpendicular bisectors? Are we cool with the purple bear circus? Sweet. Let's talk about angry birds inside. So now we're going to identify and use the incenter. So here's a diagram. We're going to do some algebra. Now what's going on in this diagram? You have to be able to notice what is happening. We have 2 congruent angles here, right? And a line cutting them through. So we should be able to recognize an angle bisector when we see one. Okay? And we have to be able to do that same thing everywhere. We have to recognize an angle bisector when we see one. So look at another angle bisector. So we have all of these angle bisectors. So what happens when angle bisectors meet, right? So what's happening? So we have 3 angle bisectors. And remember, what do we do with angle bisectors? Where angle bisectors meet, we have our incenter. Okay? Remember, angry birds inside. Angry birds inside. Thank you, Miss Book. That's just awesome stuff. Okay, so remember that note. We have a purple bear circus with angry birds inside, right? So angle bisectors are the incenter. So what is the incenter? Remember I showed you with that circle, the incenter means the radius of the circle remains the same. So if you know DG, then you know EG, and you know FG. They're all the same, okay? So they all are equal. And that's where the algebra comes in. We finally can start playing with this question. If GE is 2x minus 7, and GF is x plus 4, what do we know? We now know, well, that GE, 2x minus 7, is equal to GF, x plus 4. They are equal. And that is the hard part. That's the geometry part of understanding what's going on, right? If we know GE, then we know GF, and we also know GD. Okay, so that's what's happening. It's because it's the radius of a circle from that original note on concurrency of angle bisectors. So if you're confused, pause, rewind. Make sure you understand that. The rest is algebra. We're going to solve for x. Let's undo some stuff. I've got my single x over there. I'm going to take it away on both sides, and I'll be left with 1x here, and that's minus 7 equaling positive 4. I'm going to undo a minus 7 with a plus 7, and then I have x equaling 11. But before I go circle my answer, what was the question? What is the distance from G to D, right? What is the distance from G to D? Well, what do I do with that 11? I can substitute it into either one of these. So 11 plus 4. 11 plus 4 is 15. So GD is 15. And just to check my work, guess what 22 minus 7 is? 15. Right? Hey, 22 minus 7 is also 15. So either one, it still works. So you can check your work. But either way, the length of GD is 15. And that's how that works. Cool? Cool. So let's do another. Now this particular example is a little bit more complicated looking, right? So it's giving us a QN. Here's a QN. Boop. And it's giving us a QM. Here's a QM. Boop. The question is, what is QO? And here's QO. Boop. So the question is, well, what is going on, right? What's happening here? How do we know these are all the same? Well, because we have an angle bisector here. Okay, we have an angle bisector at L. And we have an angle bisector at K. So we know where those two angle bisectors meet, that's the incenter. And we know the incenter means we have a radius there. So the QP is nothing, right? QP is a distractor. So this is distractor. We don't need it. Okay, so if we know those two things are the same, just like the previous question, we have our equation set up. We have, okay, so Qn is 5x plus 36, and that's going to be equal to Qm, 2x plus 51. The rest is algebra. So let's do some algebra. Undo my 2x first, because it's smaller than 5x. So I have 3x plus 36 is equal to 51. Now I undo my 36. And then I have 3x is equal to, let's see, 15. And then divide by 3. And then x equals 5. But before we go circling anything, we have to read the question. What is the length of QO? So we have to find out, well, what is the length of either Qn or Qm? Because they're all the same. It's all the same anyway. So I'll just substitute a 5 wherever I see it. 2 times 5 plus 51. 2 times 5 is 10. 10 plus 51 is 61. So the answer is, of course, 61 units. Does that work for over here as well? 5 times 5, 25 and 36, 51. Win. Okay? So that's using the incenter. Remember, angry birds inside. Angle bisectors, incenter. Quick quiz. So this is what you might see some questions like on standardized stuff. Given the circle with center P below, what congruent statement can you write for the inscribed triangle? Well, what's going on in this picture? Hopefully what you see is a circumcenter. That's hopefully what you see. P is a circumcenter. And you know that all of these are the same. Okay, so that's hopefully what you see. The circumcenter, so the radius is all the same. I'll finish this up quickly. That's my next class coming in. So if you look at the options, we have HP congruent to LP. HP, LP. That is true, but there's more. So we might have that, but there's more. We have GP and GL. That is not true. That goes that. How about GP and LP? Yeah. GP and HP? Yeah. HP and LP? Yeah. So this is totally true, and it's way more true than A. And it's the same thing. It's way more true than D. So all of the possible statements there are located in C. We have to use what congruent statements can you write? We can write all three. So we can write more than one. More than two, we can write all three congruent statements. And then lastly, why is that one question about vocabulary good? So here's another example of a question. A gazebo, rose garden, and a bench are located at the vertices of a triangle, just like we've seen before. A landscaper wants to build a goldfish pond that is equidistant from all three. How should the landscaper determine where to build the goldfish pond? Well, if we know it's equidistant, we can picture the triangle, right? And then equidistant would be at the incenter, and the circumcenter, and the circumcenter is found by using perpendicular bisectors. And so we look at our things. Should locate the goldfish pond at the point of concurrency of the triangle's perpendicular bisectors. That's what we know. So we know our selection should be B, right? And that's our vocabulary for the day. So hopefully this was a helpful, maybe exciting, maybe fun. At least the note from this book, angry purple bear circus and angry birds inside, right? If you can remember that, you're all set. I will see you on the flip side for more fun inside a triangle. Bye-bye.